Hello and welcome to Sound Quality. My name is Scott McDonald. With me is Pete Schuldenbrand. You want to say hi, Pete?
Hi, everyone. I'm excited to learn about sound quality today.
Yeah,
Hi.
yeah, it's going to be really futuristic and cool. Um, so we're going to talk about sound quality today, and I like to start off by kind of giving a high-level summary of what we mean by sound quality or what sound quality is. And sound quality is concerned not so much about the level, the raw level of the sound, but more about the subjective appreciation we might give to that sound. And this could be a positive thing or a negative thing. When a noise is annoying or harsh, it's less we're less willing to listen to it, right? It makes us more unhappy. Whereas if we really like the sound of a Harley Davidson motorcycle, it might be loud and some people might not like it, but that might really evoke an emotional response from us, right? It might be really positive for us. So the same sound might be subjectively evaluated by different people as being something different. And it's really talking about the more complexity of the sound rather than just the dB level. Okay, so if you think about a mosquito, for instance, Pete, you're on vacation, you hear this really faint buzzing sound in your ear and you recognize it as a mosquito. Is that a positive experience for you?
Not generally, no.
No, right? It's very, very faint. The noise is quiet, but it's so irritating because you know that thing's going to bite you and then you're going to be scratching your leg for the next week, right? And so it's not just about the level or the dB level of noise. It's really about what it makes us feel, okay? And that's what sound quality is all about. It's trying to objectify sort of our subjective evaluation of the sound, okay?
Sounds good.
So when we talk about a sound quality process, it really begins with making some measurements. We're going to talk about how we are best suited to make some of these measurements for sound quality. But those measurements can be fed through a couple different paths. And the first one is sort of the subjective listening path. Okay, so this is where we're going to listen to the recording. We might play the recording for some potential customers or existing customers and say, hey, what do you think of this sound? That's subjective evaluation. We also do some objective analysis where we're going to be doing some calculation, traditional noise and vibration, post-processing on the data, but focused with some specialized sound quality tools. And obviously there's going to be an interplay between these two branches, right? We're going to do some subjective evaluation, see what we like, then maybe go do some objective calculations and say what did we like about those recordings and try to figure it out objectively, and we're going to pass that data back and forth. But ultimately both branches are going to come together and help us hopefully improve the sound quality of our product's sound. Okay, whatever it is we like about it, we want to boost that. Whatever it is we don't like about our sound, we want to minimize those things. Okay, and we're going to use these sound quality metrics to help us focus on this objective analysis part. Okay, so the sound quality metrics we're going to talk about today are really the tools in our toolbox to help us move from our subjective impressions to some objective, hard and fast numbers. Does that make sense, Pete?
It does. And Scott, does sound quality matter to a company's bottom line? I mean,
Oh, for sure. I mean, you think about if no one likes the sound of your coffee grinder. Let's say you make a really powerful coffee grinder, but it makes this horrendous, irritating, squealing noise when you run it. It might grind coffee better than anyone else on the market, but are you going to want to buy one of these and have it in your home and use it every morning while your kids are trying to sleep?
yeah, and I guess in today's age with all these online reviews, people will instantly light up the internet like this thing.
Oh, yeah.
It's horrendous. It's scaring my cat or whatever.
I can already see the sort of still frame on a YouTube review channel with blood coming out of the ear or something, to get the clicks, the clickbait part of it. It's a huge part of companies' bottom line. There's a lot of interest in sound quality. It's not just about the level, but also about the subjective impression of using that product, right? So
yeah, I guess we don't want customer complaints or warranty turn-ins and things.
Yep, exactly. So I got a quiz for you, Pete. If we're going to be doing some sound quality data acquisition, and we're going to stick to that sort of left side of the branch, we want to specifically use this data for objective metric calculation. Which of these two common data acquisition tools do you think I want to use? This binaural head, that where the microphones are inset into the ear and there's the head and everything is part of it and records left and right ears simultaneously, or just a good old-fashioned half-inch microphone? Which one should I use?
Well, it seems to me that the binaural head is much more fancy, must mimic human hearing better, so probably a binaural head, right?
Well, that is true. It does mimic the human hearing ability a lot closer. The problem is it's not the tool we want to use for metric calculation for sound quality. And the reason we want to use this microphone over here is because we've been doing sound quality metric calculation for longer historically in the field of acoustics than these devices have even existed. Okay, these are relatively new kids on the block in terms of data acquisition tools for acoustics. And so historically all metrics have been calculated based on a single microphone. Okay, and so we're going to want to put ourselves and set ourselves up for success and use the microphone for data calculation or for data acquisition, specifically for sound metric calculation. Now, as we're going to find out, we also, want to set ourselves up for success in that other half of our sound quality process. For the subjective evaluation, we definitely want to be using this binaural device because it records sound so much closer to how we actually experience the sound, as you said. So your instinct was right. It's just specifically about the sound metric calculations that we need to be careful. But ideally, we'd like to have some ability to move data back and forth between these two devices, right? Maybe I don't have both devices and I can't repeat my test, so I have to take one or the other. It'd be nice to be able to take data with the binaural device and make it possible to calculate metrics, right? Wouldn't you say that'd be a nice thing?
Yeah, and I imagine there's a difference in cost. The head's maybe a little bit more expensive than the microphone, so
yes, for sure.
Be good to get started, with something that's a full.
Yes, absolutely. So this effect we're talking about is if we have the same sound source shown here with this little speaker icon, and we record that sound with a half-inch microphone and one of these binaural measurement devices, it's important to understand that I'm going to get two different answers, okay? And we're just showing them in different colors for illustrative purposes, okay? But the half-inch mic is going to give me this blue answer, and the binaural device is going to give me this green answer in the frequency domain. And this one's going to be called what we'd say is field affected, okay? It's because the presence of the head and torso shape in the acoustic field, actually taking up space in the air, that the head and torso shape actually affects the way that the sound is perceived and recorded by this device, okay? And this mimics how we would hear it if we were standing there, and essentially we would be playing the dummy. Our head and our torso are always in our acoustic field, and so these devices that measure binaurally actually capture our experience a lot better or more lifelike manner than the half-inch microphone does, okay? But the difference between the blue and the green has to be understood, and if we're using one or either one of these devices, we have to know that this effect is happening if we're going to do things correctly, okay? And the difference really comes down to, am I doing analysis, metric calculation, or am I just listening to the data, okay? So if I use a single mic, I'm all set up. I'm perfectly set up to do metric calculation, traditional noise and vibration, processing, FFTs, things like that. 100% good to go. If I use a binaural device, I have to know that I'm going to end up with a field affected recording, but this is perfect for headphone playback, for listening. How does it make me feel? Let's use it for our jury test. It's ready to go. If you want to try to move from one to the other, let's say we take some data with a binaural device, but we really want to do some metric calculation on it, there is a process we can follow where we're going to sort of adjust the frequencies and the amplitudes of our binaural recording and hopefully end up with an approximation of this blue single mic recording. And this process of applying this equalization is called equalize for analysis, right? So we take a binaural recording, but we want to use it for analysis. So we run it through this process called equalize for analysis. Okay, so the data gets stored as the blue half-inch mic recording, but now we want to play it back. We want to listen to it. We can actually reverse this process, apply the FRF in the opposite direction, and now we get back to this sort of field affected data, and we can listen to it again. Okay, so I can kind of move back and forth from a binaural device to a single mic piece of data, and then reapply that equalization for playback, and we get that field affected sound, and we'll get the lifelike recording played back for our playback. Does that make sense, Pete?
Yeah, so I think what you're saying is, the microphone and the binaural device record the same sound over the same frequency range, but the levels would be different depending on the frequency, because the torso interferes with the sound, or if you're wearing a headset, your face does, or whatever. So you can actually adjust the levels to be closer to the single mic or vice versa.
Exactly. That's exactly what we're doing. Yep. Just a frequency amplitude correction, we call it.
Is there a correction for bald guys versus guys with hair like you?
I'm sure there is, but all of that sort of gets lumped together. This is obviously an approximation for different shapes and sizes of human beings, but it's the best that is available.
Okay.
So when we get into equalization for replay, so now we're going to take this data. Obviously, when we store the data, we want to store it without the head and torso, so we call this equalization for analysis. We're ready to plug it into our test lab and do some metric calculation. But now we want to play it back, right? So now we're going to reapply that thing that we removed, the head and torso. But there's a second stage to this that often gets forgotten, and that's equalization for the headphone we're using to play back the sound. And this is called replay equalization, because all headphones are not even made equally, right? And there are no perfect headphones out there. And so even the device we're using to play back the sound that we so carefully recorded is going to have an effect. And I'll show you an example. So this is an FRF, or a frequency response function, for the Skullcandy Rock Nation Aviator, and you can see the effect that the headphones themselves are having on the frequency response of the sound that we're playing in. So if we know the headset we're going to use, we can actually account for the effect of the headset and replay in a really truly lifelike manner, and account for this in our playback. Okay?
And the whole goal is to make it sound to us when we listen to the recording like we're actually there.
Absolutely. Yep.
Okay.
Exactly. So how does this equalization process manifest itself in Simcenter Test Lab? Well, the sort of easiest and most straightforward approach is to take your own data and use a Scatus XS with a binaural headset. And if you do that, all of this equalization is sort of handled for you automatically. The data is stored using this equalize for analysis, and then when you replay on that device, it will be replayed, equalized for replay automatically. But we know not everyone has their own binaural data acquisition systems, and maybe they're having to process or work with sound someone else is providing to them. So we give you some tools in both Simcenter Test Lab Classic and Simcenter Test Lab Neo to do this equalization after the fact. Okay, so in the Scatus XS world, you take your data, it's automatically done for you, both in the data storage half as well as the replay half. But let's say someone sends you a binaural recording from another system that isn't equalized for analysis. Well, in Simcenter Test Lab Classic, you can use this time signal calculator function, equalize for analysis. This will actually ask you for the type of binaural device that was used to make the recording. So if it's a Model A versus Model B, we can specify how we want to correct for those different types of binaural transducers. Okay, and if you have a unique one that isn't in our list, you can actually create your own FRFs and store those in Test Lab. And this process is exactly the same in Test Lab Neo, where we have an equalize for analysis method we can add to the process builder. Okay, so this these tools in Test Lab and in the Scatus XS allow us to do this equalization both for data acquisition and playback in a really seamless and easy to use manner. Okay? So now we're going to talk specifically about some of these sound quality metrics, which are tools we use to separate our different aspects of our subjective opinion. Okay?
These are ways to quantify sound that are different than decibels, like one of the traditional ways. Is that right?
That's exactly right. Decibels is sort of the original sound quality metric, if you want to think of it that way. It was the first kid on the block, and just, what's the pressure level? But as we're going to see, decibels have some shortcomings, and specifically when we're talking about our perception of level. And we have actually a whole family of metrics called level-based metrics that are all about this. And the first one we're going to talk about is loudness. But it's important to note that there are different types of sound quality metrics. We're not going to talk about all of them today, but transient metrics are specifically formulated for short time events like clicks and pops, sounds that come and go really quickly. We need different approaches for those. Those are transient metrics. In the second half of our talk today, we're going to talk about these tonal metrics for sort of single frequency sounds. Those are typically more annoying to a human listener, and so we have some specialized metrics to work on those. And then modulation metrics are about sounds that sort of modulate or come and go versus time, some wah, wah, wah type phenomenon. We want to look at those maybe a little bit differently than we would some other sounds. Okay?
The
So we're going to start out.
wah of the modulation metric sounds like a good one to quantify my kids.
Yes. Yeah, I totally know what you mean. Level-based metrics. So these are, very simply, is it more or less than another sound in some discrete manner? We're going to talk about loudness. We're going to talk about something called AI, or Articulation Index, and then I'll close up with something called Sharpness. And these are used in industry all the time. Articulation Index is used by J.D. Power for their assessment of automobile interiors and how quiet they are. When they make their recommendation, they'll use Articulation Index. And then something like Sharpness is very often used for a balance between the road noise in a passenger vehicle versus the wind noise, and how much of what you hear is balanced between those two sources. Sharpness is one of the tools we have at our toolbox to help us separate maybe these two similar sounds, but they're subtly different, and Sharpness is one of those tools we can use. Okay? So loudness. Pete, if I said I have two sounds, one's at 40 hertz, one's at 400 hertz, but they're equally loud in terms of sound pressure level, same level, with our microphone, does one of those sound more loud to you, or do you perceive one as being louder? What do you think?
Yeah, I think so, because I know humans in general, all of us, have trouble hearing lower frequencies compared to higher frequencies. So I would guess that the 400 hertz would probably sound louder than the 40 hertz, even though it's at the same pressure or dB level.
Absolutely right. That's right. And this is sort of hearkening back to another sort of basic sound quality metric tool that we have. You may be familiar with it. It's called the A-weighting filter, right? The microphone we use to make a sound pressure level measurement is built specifically to be able to hear all frequencies equally well. Human beings don't have the same trait, and so we use an A-weighting filter to sort of weight or adjust a microphone recording to make it more representative to how a human being would hear that sound. And like you said, we don't hear as well at low frequencies, and so the A-weighting filter is going to artificially adjust the magnitude of that 40 hertz, and it's actually like more than 30 dB less loud, or in terms of level, than that 400 hertz tone. Even though they start out the same sound pressure level, a human being standing there is going to say the 40 hertz one is like 30 dB quieter. Okay, so that's A-weighting, but it's really used to capture this effect of the human hearing. Now, if I said we supercharged that sort of idea and we created this family of curves, these are the curves of equal loudness, and they take that A-weighting idea and they just sort of take it to the next level. Okay, so we see it's not just one curve, but a whole family of curves. And you see it's not just a simple, arc through the frequency domain. It's got these ups and downs. And that's because our human hearing ability is actually much more closely related to the way these curves are shaped than the A weighting curve. The A weighting curve was used historically when they were making a mechanical filter, and so they had to build it with resistors and capacitors and things. And so they had to sort of choose a rather simple curve to be able to apply that A weighting curve.
Yeah, this
filter.
curve looks a lot more wavy than that A weighting curve. So
Yes. Yep.
Mimic human hearing a lot better, I guess.
Yes, that's exactly right. And so you see sound pressure levels on the y-axis and frequencies along the x-axis here. And what these curves tell me is that if I've got a 100 hertz tone, and let's say it's about 50 dB here, and I've got another tone at 30 hertz, but it's all the way up at 80 decibels, so 30 decibels of difference in terms of sound pressure level between these two. The fact that they're both touching this same blue line tells me that a human observer is going to perceive these two tones as being the same loudness. Okay, so 30 dB apart, but they're equally loud to me or you standing there because they touch this same line, which I'm now showing in magenta. And that's how these curves work. This magenta line is actually the definition of a new unit for loudness we're going to call the sound. Okay, so sound pressure level is talking about the actual oscillations in terms of pressure in the air that we're hearing, but this unit sound is going to say my whole purpose in life is to tell you how loud you're going to perceive that sound pressure level. Okay, and you notice this sound is a function of frequency, right? It's not a single value at a single frequency. It goes up and down, and that's going to come to our advantage and make it a much more helpful unit to use for perceived loudness. Okay?
So yeah,
Now,
the low frequencies have to be at a higher level to be heard as well as in the middle range because of the way we hear.
That's right. Yep. Now, kind of a rule of thumb, Pete, in decibels, you may have heard as like in decibels, we'll perceive a sound as being twice as loud after it's increased by 10 dB. Have you ever heard that?
Yeah.
Okay, so if I said here's 30 dB and I'm going to make it twice as loud, I got to make it like 40 dB essentially before you'll say it's twice as loud. Now, if I made a promise to you that this SON unit is going to take care of all the awkward back of the envelope rules of thumb you had to memorize about decibels, and I said the SON's going to solve all of that and make your life easy, what do you think the SON value is for something that's twice as loud as one SON?
So instead of like 30 to 40 to 50, could it be as simple as one SON going to two SONs and it's twice as loud?
That's exactly right. I
my
told you this
gosh.
SON value is going to solve all your loudness problems. It's going to make
Oh, it
life
is.
so easy for you. It's going to be like you're on vacation all the time.
I couldn't keep track of all those dB rules.
Yeah, forget them all because the SON's going to solve all those problems for you. So, two SONs is exactly twice as loud as one SON. And if I said I doubled two SONs in terms of loudness, what do you think that SON value is?
Well, double better be four SONs, or
And it is. And here's a cool thing. If you notice, right in this frequency range right here, what's the decibel value difference between one SON and two SONs and four SONs?
it looks like it's 10 dB. But
Yeah.
yeah, if I look over, you pointed to the left there, they get a little closer than 10 dB at low frequencies. So
That's right. That's right. So that's a rule of thumb in the decibel world because it doesn't hold for all frequencies. So that's why it's a rule of thumb and not a rule. But if you look right in this frequency range here, it does hold true. And these are, we will come to learn, as very important frequencies for human hearing. But you notice if I just talk about SON value, I don't have to worry about a frequency value anymore because one SON is one SON and two SONs is twice as loud no matter what the frequency is. Okay?
SONs are not dependent on frequency at all, whereas decibels are, huh?
That's right. Yep. What's half as loud? What's half as loud as one SON?
Half as loud? How about half a SON?
Boom. Half again is a quarter SON, eighth of a SON's down here, and then this dash line is the threshold of human hearing, and it's such a small SON value, like a 16th of a SON, we don't bother even even keeping track. Okay, and below that we can't hear it. Okay,
All right.
so that's this new unit, sound. Now, in decibels, in terms of sound pressure, there's this odd thing where if I actually went from 1 Pascal to 2 Pascals, my sound pressure level is going to go up by 6 dB when I convert to decibels. And so a doubling of sound pressure is 6 dB change. But we just talked about this. It's really 10 dB change when we perceive a doubling. And so there's just this odd nature about decibels. And so we'd like to leave it behind and forget all about it. And that's where this loudness zone value is going to come in. It totally linearizes the human perception of loudness. So again, 2 zones is twice as loud as 1 zone no matter what. And 4 zones is twice as loud as 2 zones. And if I said something's 30 zones and it used to be 20 zones, I can legitimately say it's now 1.5 times louder than it used to be. Because it used to be 20, now it's 30. 20 times 1.5 is 30. So it perfectly linearizes all of this math that we have to do. And the coolest thing about it is that this frequency dependency of human hearing, that sort of undulating curve that we saw, all of that's built in. All I need to tell you is it's so many zones, and you have all the information you need in terms of loudness.
That's good.
Cool?
Yeah, that's very cool.
Awesome. Well, I sent you some data. Can you open up TestLab and let's take a look at that? And we'll do a little demonstration here.
Sure, you're going to make me prove what you just said is actually true. Thanks.
I want you to experience it firsthand. I don't want you taking my word for it.
All right. All right, Scott. So I think you sent me some vacuum cleaner data. Is that right?
That's right. Vacuums A and Vacuum B, 2 recordings.
Vacuum A and Vacuum B.
Yeah, why don't you take a listen to them right now and see if you think one of them is louder, and if so, which one, okay?
All right. Let me do, yeah. I'll hit play. A. B. Well, Scott, I think A sounds louder than B, and it's got a bit of a shrill thing going on.
Yeah, they certainly sound different, right? You wouldn't mistake one for the other, but
No.
A sounds like it's louder to you than B.
Yeah.
Okay, so if you were gonna, start doing some traditional analysis, what would you start looking at for between these two?
Well, I think I would start by looking at dB. So here's
Right.
A's dB level, 95. And that's pretty damn close to 95 too. So it looks like A versus B, they're about half a dB, a sixth of a dB different. That doesn't sound like very much difference in the world of dB.
Yeah, it's not enough to make a appreciable difference in terms of decibels. Usually, a rule of thumb for decibels is perceivable change is about 3 dB. So half a dB, we're not able to discern the difference there. So decibels aren't working for us, right?
Yeah. Should we try something else?
Yeah, we're going to try this zone. I'm telling you, it's going to solve all your problems. So yeah, just like you added the decibel sound pressure level there, add that loudness
All
unit
right.
to your legend.
Is 114 zones, Scott, and B is 100 zones.
Yeah.
114 versus, so that's about, I guess, 15% different, or whatever that works out to be. That kind of tracks with what I heard.
Exactly. I told you it was going to solve all your problems.
Yeah.
So zones captures your perception. It gives you an objective number, like how many percent difference or how much louder B is than A. So let's say we work on vacuum cleaner A and we want to make some improvements. When you look at that average spectrum.
Yeah, I noticed there were some tones there. And I guess with this software, we can go in and, grab a cursor and we can actually do some filtering on it.
Yeah, and that filter will actually do the calculation again for us and show us what the improvement is, loudness before and after.
Yeah, and B didn't really have tones, but A definitely did. So it looks like, well, at this instant in time, it's 120 zones, And taking out that first tone there, it's going to get it down to 100 zones. A will become closer to B.
Yep.
I'll turn the filter on and off. Yeah, you can definitely hear that shrillness to the whole thing.
Absolutely. So before you've worked a minute on this vacuum, you can tell there's going to be real benefits to solving that tone, and exactly how much that tone will help you.
Well, yeah, that if I could get rid of that tone, I'd be close to B and perceived loudness. I should see what this tone does. That doesn't look like it's doing too much, huh?
No, very little. But again, the sound value takes into account the frequency of that tone. It's up at 11 kilohertz.
Oh.
That's at the edge of the hearing ability, and so the tone there, we don't even perceive it coming and going.
Yeah. So this is what's good about this is I don't have to even bother to go after this. It's not going to improve my sound. I just have to go after that first peak.
Yep, it's scary looking because it's a big high amplitude peak, but Sones is helping us understand we don't even have to worry about it.
Sweet.
Very cool. Awesome. All right, so that's a little bit about Sones. So I want to talk about some other effects with human hearing and just touch on them briefly. How long a sound is present actually affects how well we hear it or how loud it's going to appear to us. So if I showed you the three traces here, red, green, and blue, all I've done is played them for a longer amount of time each time. So you see red I played for 0.01 seconds, green I played for 0.05 seconds, and then blue I let it play for 0.3 seconds. Now if I look at a sort of a spectrum map here, so this is sound pressure level versus frequency versus time, you see the sound pressure level is identical, right? The microphone and the software sees the sound pressure level instantly. It doesn't need any time to build up, right? So the decibel level is exactly the same regardless of how short the time the sound is there, but the human hearing system does not respond instantaneously. And so if we now calculate a time varying formulation of this loudness metric, it's built specifically to respond in time very, very similarly to how our human ear does, okay? So you see the 0.01 second sound only registers 27 sounds. I let it play a little bit longer, and now it's louder to us, and it'll actually be 34 sounds. And then if we let it play all the way for 0.3 of a second, we give it 47 sounds. So you see this build up of loudness versus time, and this is again formulated this way to capture the human hearing ability and how quickly we can respond to short versus long sounds. Okay.
Wow.
So this is another application of loudness.
Not only is it frequency dependent, it's also time dependent, our perception.
That's right. That's right. And there's something else going on in here that's even, I think, cooler, and that's something called masking, and this is frequency masking. Okay, so listen to this, Pete. So this orange dash line, let's say that's the threshold of human hearing, okay? And so in order for a sound or a tone to be heard, it has to pierce through that threshold, right? So if I've got a 4 kilohertz tone and it's, higher in amplitude than this orange line, you would hear that as a pure tone and it would contribute to the loudness, okay? But now I'm going to introduce a second tone, lower in frequency and higher in amplitude, all the way up here at about 100 dB and 1200 hertz, okay? What the research shows is that this lower tone actually sort of distorts this human hearing threshold, and so you see this 4 kilohertz tone no longer crosses that dashed line, and so our brain is no longer going to hear this 4 kilohertz tone. It's going to disappear to our brain. And if I played this setup for you, you would say this captures your perception exactly. What we want to do is we want to have TestLab be able to comprehend this change as well, and we don't want to be, including the loudness of this 4 kilohertz tone in our overall SON value because our brain's not going to hear it. I don't want it to contribute to the loudness, okay? And so this ISO standard that we use to calculate that SON value, or rather that you just showed us in TestLab, actually includes this effect, okay? And so the presence of each of these tones is actually masking some of this other frequency content right next to it in the frequency domain. And that calculation that you did in TestLab actually brings this effect into account. Isn't that cool?
That is really cool. I guess that's why people buy like things that make the sound of the ocean so they can sleep at night. It'll mask other sounds and things like that. Not only, I guess, is it soothing, but I forgot that I guess sound does mask, and if you have a good metric, it needs to take it into account.
Yep. It's happening in our brain, so it should happen in the metric, and ISO 532-1 does include this effect, so pretty cool. So loudness, just to sum up a little bit, it's a psychoacoustic parameter, kind of what we would call the volume, or how loud a sound is. And it is standardized in some of these standards. There's an ISO, a DIN standard, and then an ANSI standard, all sort of mirroring each other. And they will consider all things, including the frequency of the sound, the level, the hearing threshold of the human being at that frequency, but also the temporal effect that we talked about, as well as this frequency masking that goes on. Okay, so that SON value is really pretty sophisticated, and like I said, it's going to solve all your loudness problems. Okay, so I want to show you also in Simcenter TestLab Neo, we can actually do both that stationary loudness as well as the time varying loudness. So why don't you open up TestLab again, and I'll show you with those two vacuums, and we'll take a look at how these methods work in TestLab.
Sure, we can start right where we left off, Scott, and hopefully you can guide me a little. I haven't used the processing too much.
Okay.
So
yeah,
I have the processing added in, and these are the
Great.
vacuums. So you just say like add to input basket, or
yep. We want to work on
sounds.
that data.
Just A
Yeah,
and B,
just
I guess.
the raw timed histories. Yep.
Okay.
And go down to that processing tab that you added, and this is called the process builder. And what we can do is in our input basket are those two time recordings, brand A and brand B, and now we essentially want to build a little flow chart and send that data through some processing capability. Okay,
This has got to be really complex to do all that stuff, I bet. How do I create a flow chart?
Pretty hard. It's pretty hard. I just want you to start typing on your keyboard and type the word loud.
Loud, okay.
Boom. You see, you filtered out all the other metrics. We really just want to do loudness stationary and loudness time varying. You can drag and drop those boxes right there. And then all you have to do is go up to your input little box there and then drag and drop that arrow right to, there you go. They're connected. And so now all those vacuum cleaner recordings are going to get sent through these two different processes, and we're going to get two different answers all at the same time. So hit that big run button at the bottom left.
Wait, where's the complex part?
You're watching it happen. It happened behind the scenes while you were asking. So
Holy
yeah,
crap.
over there in your active analysis, you see you have a couple different results. So that's the time varying loudness of brand A and versus brand B.
Let me make that font a little bit bigger here. But yeah, brand A was annoying, and I can see, and louder.
Yeah.
But yeah, A is definitely louder than B over time according to the loudness. And what's
Yeah. So that
stationary loudness?
Yes. So loudness time varying shows the SON level versus time. Loudness stationary is actually going to give us some idea of the frequency content of our loudness and what frequencies are making our product louder. And so if we look at brand A and brand B here, and so stationary loudness shows us SON level versus bark band. And bark band is just this fancy way of looking at the frequency spectrum. So you see brand A in red there and brand B in green. And you see that brand A in red is louder at a higher frequencies than brand B is. And brand B is sort of kind of flat, right? It's equally loud in the low and high ends of that bark bands. And that's why it's a little bit easier for us to listen to, right? It's more balanced in terms of its frequency content.
Yeah.
And stationary loudness tells us that.
This is higher frequency, so yeah, that's maybe why it's shrill, I guess. Cool.
Yep. Exactly.
Wasn't as hard as I thought. Thanks for guiding me there, Scott.
My pleasure, Pete. All right. So I'm going to jump back over here. So just to sum up, loudness, again, expressed in sounds, gives us this nice intuitive way of working with volume or loudness for perceived loudness. There are some different standards. And then on these summary pages is a link to our articles on the community. So the Simcenter Testing community is a great place to find information on all of these topics we're going to talk about today. And I'm going to give you a nice little quick link to each of these articles, and it'll go much more in depth than we have time today. So check it out. You can play some sounds, listen to the vacuums yourself, and learn more about it. So AI, this is our second level metric. This is called Articulation Index, and its whole purpose in life is to give us a single number that sort of sums up how easily we'll be able to talk to each other given the noise in the background. Okay, so if you and I are flying an airplane and we need to communicate to each other, but it's loud in the cockpit and we don't have any headsets, it's old, maybe we forgot our headsets at home, and I want to know how easily am I going to be able to tell my co-pilot Pete to put the flaps down. Well, we could make a recording of the noise in the airplane cabin and then analyze it with Articulation Index, and it would spit out a number. And the higher that number is would tell us the more easily we're going to be able to communicate and understand each other. The lower that number is, it's going to tell us how hard it is, or it's going to be harder. Okay. And the way this is set up is it's essentially looking at a frequency band. You see it's 200 to 6300 hertz. And most of the information in human speech is contained in this frequency band. Okay, and so we're only going to look at those frequency bands. And essentially we're going to weight the background noise in each of these bands and give it a score. Okay, so essentially you see this articulation window. You see these frequencies between 200 and 6300 hertz. And the weighting factor is shown here in the third column. Okay. And you see these frequency bands right around between 1,000, 2,000 hertz are the most heavily weighted because those are the most critical. Okay, and these, the contribution to the lower and higher ends are less critical. And so the way this works is we look at the noise level in each of these bands, and we then sum up the totals for each of these bands. So if I look at these weighting factors, each of them contribute, their own amount. But if we sum them all up, we get 100. Okay. And so what this articulation window tells us, if it's at or below this green level, we're going to multiply this weighting factor by 100% or 1. If you're up here at the red end where it's 0%, we're going to multiply your weighting factor, your contribution, by 0, and you're not going to contribute to the AI. Okay, so let's take a look at a couple examples and see how this metric works. Okay, so let's say this is my background noise in my airplane cabin with Pete, and I measure the blue levels at all of these octave bands. How does this AI computation work? Well, they're all above this 0%, so we're going to take each of these weighting factors, multiply them by 0, add them up, and I'll get a sum of 0, right? So my articulation index is 0 here, okay? Because all of my octave bands are above this 0% line.
So those blue lines, Scott, those are the levels of the background noise in the cabin. So it's not me talking. It's you just record what's in the cabin, and because they're so high, nobody could speak in that cabin and be understood. That's kind of what you're telling me.
Exactly right. articulation index of 0 means you will understand 0 of what I'm saying and vice versa.
I just have to get for my cubicle when we return to work.
Yeah, it's going to be low, trust me. So now, when you're out of the office on vacation, this is what the articulation index looks like in our cubes. It's nice and low level of background noise. All the levels are below our lower limit, so we're going to take all of our weighting factors and multiply them by 100% or 1, and we sum them all up and we get an articulation index of 100. So when you're gone, I turn to our colleague and I say, hey, where do you want to go for lunch? And he hears everything I say because the articulation index is 100 and the background noise is so low. Okay?
All right.
And now maybe it's early in the morning, you're back from vacation, but you haven't had your cup of coffee yet, and so you're not fully awake, and so this is what we measure for the background noise. And we're about halfway between the 100% and the 0%, and so we're right in the middle, right? And this will mean we multiply all of our weighting factors by 1/2, and we sum them up and we get a 50, articulation index of 50%. Okay? So all we're doing is looking at the level of each of these bands, seeing what percentage between 100 and 0 it is, and then going to our table and summing up our multiples.
And it's always measuring what you consider to be the background sound, right? Like
Yep, nobody is talking in these measurements. That's right. So if we measure this in the background noise of our office, you see we've got 6 bands that are up here, but all these other bands are below the green. So our multiplication would come out like this. All these bands that are below the green line get multiplied by 1, but since all of these 6 bands are up here at the 0, we don't include those. Sum up all of these terms, and we get 43%. So what this background noise tells me is that it's loud in the most critical of frequencies for us to communicate, and so I'm going to understand just less than half of what you're saying and vice versa. Okay? So articulation index is a measure of how loud the background noise is and weights certain frequency bands differently than others. Okay? So why don't you show us how this works in Test Lab?
all right.
And I sent you another recording. This one is a helicopter flying by.
Does it look kind of like this?
That's it. Yep.
Were you like out
And
on
so
your
in this,
porch or something and it came overhead and
yeah, yep. Now in this recording, I will tell you, it's a little bit different than a traditional AI calculation because there's a guy talking. My neighbor is reading the newspaper, but it illustrates the point. Okay, the helicopter is in the distance. You're going to hear it get closer and closer. And as the helicopter gets closer and the background noise goes up, the articulation index is going to drop, and we're going to stop being able to hear my neighbor. We're going to be able to understand what he's saying.
is
Okay?
this
So you just
complex calculation again? Should I put this in the input basket and go here to do the AI?
yes, sir. And then start typing in articulation or index. Boom, there it is. Drag and drop. Connect your lines and hit run. Boom. Already done. Yep.
Boy, I'm like a sound quality expert without trying or something.
You're doing a great job.
And we want to take a listen to this.
Yeah, sure. Put a cursor on that AI plot and see if we can follow along. There you go.
That's the percentage there, huh?
Regular offense, 19 first downs with no huddle, 90 total yards with the regular, 306 without it,
So it's getting harder to understand what he's saying.
21 points with no huddle. They probably won't use the full time as a football goes to don't be surprised if the Lions start making a lot more use of the no huddle
Yeah. So
Yeah.
as the background noise goes up, the AI goes down.
Yeah, that's, high levels. Can't understand what's being understood.
That's
Hey,
it. That's
you
it.
live in there, Scott.
Yeah. It's not easy, but somebody's got to do it. Okay, great. So again, summarizing articulation index, it's a weighted average of the conversation frequencies or frequencies most important to verbal communication. There are no voices as part of the analysis. It's really just a measure of the background noise. And here's an article all about it. You can learn more about AI, but I think you'll find it very useful. Okay, so sharpness, finally. Sharpness is a metric aimed at helping us understand the balance of the frequency content of our noise between low frequency and high frequency, okay? And so the more biased toward the high end of the frequency domain our noise is, the more energy that's out there, the sharper or the more sharpness we're going to calculate with this metric, okay? So I'm going to play a couple of sort of standard signals for you here, pink noise and white noise. And these are just standard test signals that have different frequency distributions, okay? So I'm going to play these two, see if one sounds sharper or has more high frequency content in them between white and pink, okay? Okay, did you hear a difference there, Pete?
Yeah, it sounded like white was a bit sharper to me.
You sure did. And the white noise calculates more sharpness because it's got more frequency content of higher amplitude out here at the high frequency end. Okay.
Oh, well, I see pink noise keeps
And we
coming
use this
down.
value of ACUM for sharpness. And there are several standards that we use to calculate sharpness. And we'll cover a little bit about those differences here. So sharpness, if we look at the calculation, and this is for the Din and Zwicker formulations, we'll use this formula here. Sharpness is this term here. And if we break this down a little bit, we see that these two terms are identical. And we're really looking at the total loudness kind of broken up per these bark bands. So again, bark bands are just sort of ways of breaking down the frequency spectrum into these groups. Higher the bark number, the higher in frequency it is. So we just look at the total loudness across the frequency spectrum, and then we normalize it to make it come out so that the definition of 1 ACUM is 1 ACUM. But then we have this weighting factor, right? And this guy is a function of frequency or bark band. And you see I've got two traces here for Zwicker and Din. And essentially they penalize higher frequencies. The higher the bark band is, the higher in frequency. And so we weight the noise content out in these higher frequencies with more sharpness. Okay, and you can see Zwicker and Din approach this weighting function a little bit differently, but both are doing the same generic thing, where as we go higher in frequency, the more sharpness we attribute. Okay?
I guess
Orays,
the thing is sharp, it might seem a little cheaper because it's got a lot of high frequency, like tinny or clacky.
yeah, very possibly, yep.
Yeah, okay.
Typically, the more high frequency, the less pleasing the sound is to us, yep. There's a third formulation based on the research of Orays, and he has the same approach here, where we're looking at the total loudness distribution. We have a weighting function. He's got his own normalization constant. But his weighting factor is actually also a function of the loudness of this, the sound that we're playing. Whereas Zwicker and Din, if I have a 100 dB sound and a 50 dB sound, but the frequency content's the same, they will calculate the same sharpness. Orays does not. Orays realizes that the louder the sound is, the more sharp a given sound is going to be. And so he incorporates the loudness of the sound right into his weighting factor. And we show that here. So for this piece of data, it gets louder versus time. If we calculate Oray's sharpness in red versus Din and Zwicker, shown in blue and green here, you notice they are sort of flat or constant versus time, where Oray's sharpness continually increases versus time as our sound gets louder. Okay, so they're all trying to do basically the same thing. Oray's just takes into account how loud the sound is on its own. Okay.
All right.
So Pete, I'm going to have you do one more demo for us. I let's go back to those vacuums since they work so well.
All right, Scott. Yeah, so I'm right where we left off. Can I actually try this? Let's see if I can catch on how to do it. You want me to calculate sharpness for these vacuums?
Yeah.
All right, I'm going to type in sharp.
Boom.
And I'll connect that. And did you say Ores was...
Ores is a good one. Yeah,
All
you
right.
can try a couple of them if you want, but Ores will take into account how loud the recording is.
I'll hit calculate here.
Boom. And now we're going to get all of our loudness results plus our sharpness results.
Yeah, in fact, it would be interesting to see how loudness compared for brand A and brand B versus sharpness. So, oh yeah, brand A was definitely shrill, and I can see that in the sharpness. And you said that's probably due to the fact that these higher frequencies were pretty big.
Yep. Yeah, it all has to do with that loudness distribution, and A's loudness is more concentrated in the high frequency end, and so it's going to be a higher sharpness value.
Cool.
That's exactly right.
Thanks, Scott.
And it's penalized a little bit because in the upper right, brand A is actually louder than brand B, and so that sharpness value is even higher than it would be if we had calculated with DIN or Zwicker, but the same sharpness trend would have held in either case. Pretty cool, huh?
Yes, very cool.
All right.
I'm learning something.
Well, that's good. That's the whole point. Okay, and to sum up on sharpness, the unit is acum. There are a couple different variants, Zwicker and DIN. Very similar, just a little bit different in their weighting functions. And then Ores, again, very similar, but the louder my sound is, the more and more sharpness it's going to calculate for it. Again, we have a whole article in the Simcenter community all about this, so check it out. Well, Pete, that takes us to the end of our first section here on sound quality level metrics. I want to send my appreciation to you for doing all the demos there. It was great. And hopefully you realize sounds are the key to happiness in all of your future.
Oh yeah, sounds and sharpness and AI. I'm ready to and raring to go. Thank you, Scott.
Awesome. All right, well, meet me back here after the break, and we're going to talk about those tonometrics. Deal?
It sounds great.
All right, thanks, Pete.
Yep.